In this video, we're going to present the important result that the set of regular languages is exactly the set of languages that can be described by regular expressions. In other words, if a language is regular, then it can be described by some regular expression. And likewise, if you've got a regular expression, it is describing a language that is definitely going to be regular. Here's the theorem that we're going to discuss in this video. A language is regular if and only if some regular expression describes it. Okay, we've defined previously what regular languages are and what regular expressions are. Okay, a language is regular if and only if it's recognized by some finite-state machine. So this is how we define whether a language is regular or not, if there is a finite-state machine to recognize it. And we have already showed that non-determinism and determinism are equivalent in their power, that it doesn't matter whether we've got a non-deterministic finite-state machine or a deterministic finite-state machine. A language is regular if and only if it is recognized by a finite-state machine of any sort. And now we've also defined regular expressions and the language that each regular expression describes. Okay, so in our previous slide from a previous video, we talked about for every possible regular expression, what language does that regular expression describe? And we gave a recursive definition based on the syntax of the regular expression that shows exactly which language is described by that regular expression. Okay, so we have our definition of regular languages, we have our definition of regular expressions, and now what we're saying is that these two things are exactly equivalent in power. So to summarize everything, we're saying that the class of languages recognized by deterministic finite automata and by non-deterministic finite automata and described by regular expressions is exactly the same. Okay, they all have equivalent power. Okay, they're describing the same class of languages. So one way to remember this is regular is regular is regular, whether it's described by a deterministic finite state machine or a non-deterministic finite state machine or a regular expression. If you've got any one of these three, you can convert it to the other two and get a description of the same exact language. The equivalence of regular languages and regular expressions is an if and only if theorem. So we've got two directions to prove. If a language is described by a regular expression, then that language is regular. And in the other direction, if a language is regular, then it can be described by a regular expression. Let's look at the first because it's really pretty straightforward. If a language is described by a regular expression, then that language is regular. And we've essentially proved this already, and we've already done it really in two different ways. We've shown that the union, star, and concatenation operators are closed, or that regular languages are closed under these operations. And so, by extension, our definition of regular expressions shows that the result is also regular. And the other approach is to take a regular expression and build a non-deterministic finite state automaton to recognize it. I'll talk a little bit about those on that approach on the next slide. Now, the second part of this proof, the other direction, that if a language is regular, then it can be described by a regular expression, is more complex. This part is a little bit more complex. So I'll give the outline of this part of the proof, and then subsequently, after I deal with the first lemma 1, we'll come back to this and look at it in more detail. But basically our proof approach is to, if you've got a language that's regular, then you know that there is some finite state machine that recognizes it, and in particular we know there must be a deterministic finite state machine that recognizes it. So we can start with a deterministic finite state automaton that describes the regular language. And then we show how to turn that into a regular expression. And we'll do that with something called a generalized non-deterministic finite state automaton. So I'll describe exactly what these generalized non-deterministic finite state automata are. We'll give a definition of these GNFAs, and they're slightly different than the finite state machines we've talked about. But we'll show how to turn the finite state automaton into one of these new things, and then we'll show how to modify it and reduce it. And when we're done modifying and reducing it, we end up with a regular expression. So before I do that, though, let's come back to lemma 1. If a language is described by a regular expression, then it must be regular. So to restate the first direction of this proof, that every regular expression describes a language that is regular, we have a regular expression. Okay, we can call it R. And what we're going to do to prove this direction of the proof is show how to convert this regular expression into a non-deterministic finite automaton. And since the language described by a non-deterministic finite state automaton is regular, we can then conclude that the language described by the regular expression is regular. So remember that every regular expression is made of smaller regular expressions. These regular expressions are syntactic entities. There's, sequences of symbols. And so our proof is a proof by construction. We're going to show how to construct the non-deterministic finite state machine. And so for every large regular expression, there's an operation that is outermost, and then it joins one or two smaller regular expressions. In the case of concatenation or union, there are two smaller regular expressions that are joined by the outermost operation. And if the outermost operation is a star, then it operates on a slightly smaller regular expression. So if we can we assume that we can build the non-deterministic finite state automata for the smaller regular expressions, and then we just show how to build the non-deterministic finite state automaton for the larger regular expressions. So here's an example kind of showing the idea of this construction. Let's say you've got some regular expression, you've got some outermost operator. In this case it's union, but it could be concatenation or the star operator. And you have smaller expressions that are operated on by the outermost operator. And we assume that we can build a finite state machine, in particular a non-deterministic finite state machine, for the sub-expressions. And so what we're going to show is how to take those non-deterministic finite state machines, whatever they look like, and join them or build a new non-deterministic finite state machine for the larger expression. So this is an inductive proof. It's showing how to build it, and the construction is inductive, and it's a structural induction. So it's on the we're operating on the structure of the expression. Okay, most inductive proofs, or some inductive proofs, are over the set of integers. Okay, you prove it for a basis case 0, and then you assume it can be done for case n, and you show how to do it for case n plus 1. In this case, we're assuming it can be done for we're showing how to do it for the smallest regular expressions, and then assuming it can be done for smaller regular expressions, we show how we can build a non-deterministic finite state machine for larger expressions. So this is an example of a structural induction on the structure of the regular expression. Remember that we had a definition of what regular expressions look like, and it was a recursive definition, or an inductive definition if you prefer. We showed the basis cases, if you will, a regular expression that consists of a single symbol from the alphabet, or epsilon, or the empty set. And then we also had rules that showed how to construct larger regular expressions. So for each of these, we need to show how to produce a non-deterministic finite state machine. So we'll look at the basis cases first, if it's a single symbol, if it's epsilon, or if it's the empty set. So here are the machines we construct. If our regular expression is just a simple symbol from the alphabet, we make this non-deterministic finite state machine. Actually, it's also deterministic, but single start state, single final state, single transition. Okay, this recognizes the string A and nothing else. Okay, if the regular expression is epsilon, then we build this finite state machine. It consists of a starting state, which is also a final state, and no transitions. This accepts the empty string. If the regular expression is the empty set, then we build a finite state machine that has no final states. So this thing accepts nothing. It has a starting state, but no final states, no transitions. So this machine right here accepts no strings. Okay, now for the other cases, we're basically going to use the construction that we used in the proof that these operations were closed. So you'll see the same kind of thing going on. Remember when we showed that union, that regular languages were closed under union, we built a machine that looked a little bit like this. Well, here we're doing exactly the same thing. We're adding a new starting state and a couple of epsilon edges. We're keeping our final states to be the same as they were in the smaller machines. So if you've got a regular expression that's made of a union operation and two smaller regular expressions, then you construct the following non-deterministic machine. Recursively, you construct this machine for R1 and this machine for R2, and then you construct a new machine by adding a starting state and a couple transitions here, like this. And so now you've constructed a non-deterministic finite state machine for the entire regular expression. Likewise, for the concatenation operation, remember how we join the two machines this way? Well, this is saying if you've got a regular expression that has concatenation as the outermost operation, then you can build a non-deterministic finite state machine to recognize the same language by using the machines for R1 and R2. So you first build those machines and then you combine them with a couple of epsilon edges, make these states non-final, and use this as our starting state. And finally, for the closure operation star, we build the machine that's shown here. And so this completes the proof of lemma 1. If you've got a regular expression, then it describes a regular language. And the proof is that we can build a non-deterministic finite state machine to recognize that language. And this is an inductive proof showing how to build a machine up piecemeal from the smaller regular expressions to the larger regular expressions so that it will recognize the right language. So since you can build a non-deterministic finite state machine to recognize the language, it must be regular. So the regular expression, therefore, must describe a language that is regular. So now we turn to the other direction. The other direction of the proof is that if a language is regular, then we can find a regular expression to describe it. And this part of the proof is pretty complicated. So the rest of this video is going to be occupied by giving the proof and then working through an example. And the key concept we're going to use is this idea of a generalized non-deterministic finite automaton, or GNFA. This is not exactly a non-deterministic finite automaton, but it's similar. So it's just like a non-deterministic finite state automaton. So before we go any further, we need to define what these things are. So I'm going to spend a little bit of time talking about this idea of a generalized non-deterministic finite automaton. And we'll show how we can build one of these things for the regular language, and then how we can reduce it to get a regular expression. So let's start with describing these GNFAs. As I said, they're just like non-deterministic finite state automata. They have an initial state, they have a final state, and they have edges. But there are a few differences. The edges are not labeled with a simple single symbol, but instead the edges are labeled with regular expressions. In addition, we have a couple of other constraints. There is only one except state. Okay? There's exactly one except state. And furthermore, this machine is fully populated. Okay, there is exactly one edge from every state to every other state, including an edge from a state back to itself. So we've got lots and lots of edges. We've got basically all the possible edges we could have, with the exception that there are no edges going into the initial state. Okay, the initial state has edges coming out of it but not going into it, and the final state has edges going into it but not going out of it. So other than that, other than these two exceptions, there are edges between every pair of states, and these edges are labeled with regular expressions. It's important that we understand and get a feel for these generalized non-deterministic finite automata, and so I want to work through some examples to show you what these things look like. So a non-deterministic finite state automaton has edges that are labeled with just characters from the alphabet. But in the case of the generalized machine, the edges can be labeled with very complex regular expressions. Each edge is labeled with a regular expression, and here this edge is labeled with some regular expression. Also, in our non-deterministic finite state machines, we can have multiple edges between one state and another state. Oftentimes we just draw a comma to show that there are several edges, and this is really shorthand notation, but it means there's an edge labeled A, and in addition there's another edge labeled B. Okay, so this comma represents two separate edges here. In our generalized non-deterministic finite state machine, we will only allow one edge between any pair of states. Now in this case, instead of having two edges labeled A, B, there are basically two different ways to get from this state to that state. So in our generalized machine, that same edge would be labeled A or B, okay, with the regular expression A or B. In a typical non-deterministic finite state automaton, we may be missing edges, okay? But in our generalized machine, we have full connection, full connectivity. So between every pair of states, there's an edge going in both directions. And furthermore, from every state to itself, there is an edge. Okay? With the exception that there are no edges to the starting state. So in a non-deterministic machine, we can have, here's our initial state, we can have edges coming back to the starting state, or an edge from the starting state to itself. Those are not allowed. So our machines look only like this. We have a starting state, and we have edges going to every state in the machine. Okay. Likewise, in our non-deterministic machines in general, we can have edges coming out of final states, going to other final states, or perhaps back to other states that are non-final, or even between final state and itself. But in the generalized non-deterministic finite automaton, we can only have edges going into the state. Here's another attempt to show what kinds of edges we have in these machines. Here's our initial state, here's our final state. From the initial state, we have edges going to all the states in the machine, including the final state. Here's the same machine, and these are now we're showing the edges that are coming from other states to the final state. So from every state, including the initial state, we've got an edge going to the final state. So really, this edge here is the same as this edge here. And for all states that are neither initial nor final, we have an edge going to every other state. So for example, from this state we have an edge going to this state, to this state, to this state, and to this state itself. So remember, we're trying to prove that for every regular language, we can build a regular expression. So if we've got a regular language, it means we've got a deterministic finite state machine. We also have a non-deterministic finite state machine to describe it, but we we don't need to think about that right now. We know that there must be a deterministic finite state machine. So in step 1 of constructing the regular expression, we're going to convert the deterministic finite state machine that describes the language into a generalized non-deterministic finite state automaton. And in step 2, we'll reduce it. But first, let's show how to start. So if we've got a language and the language is regular, then there must be a deterministic finite state machine that recognizes that language. So let's take such a deterministic finite state machine and convert it into a generalized non-deterministic finite state automaton. We'll start by adding a single start state. Okay? Then we'll add a single new accept state and make the previous accept states non-final. We have epsilon edges to go from our new starting state to the previous starting state, and epsilon edges from the previous accepting states to our new accepting state. Next, we will consider every pair of nodes that has more than one edge connecting them, and we'll reduce or change those into a single edge, and we will create a regular expression that is just the union of all of the different symbols. So instead of these 3 edges, we now have one edge labeled with this regular expression. And finally, all edges that are missing, remember there are a lot of edges in this generalized non-deterministic finite state automaton. For all edges that are missing, we'll add them we'll add them to the machine, but we'll label them with the empty set. So here's our machine. Previously, I had an example with a single starting state, a single final state, and 4 states that were in it. This one has only 3 here, and you can see that the 3 states are fully connected, okay, to themselves, to each other, okay, and there's an edge from all of the states to the final state, from this one, and this one, as well as the starting state. And there are edges from the starting state to all of the edges, including the final state. And so if these are the edges that we have before, we add in additional edges, as I've shown in red, as necessary, and label them with the empty set. So now we have all the edges that we need. They're all labeled with regular expressions, and we have the constraint that there are only edges coming out of the initial state, and there are only edges going into the single final state. So now we have a generalized non-deterministic finite automaton. So what we've done is we've taken the deterministic finite state machine that recognizes our language, and we've converted it into an equivalent generalized non-deterministic finite state automaton that recognizes the same language. And in step 2, what we're going to do is simplify that generalized non-deterministic finite automaton, and we're going to keep simplifying it until we're left with just a single edge that will be labeled with a single regular expression. And so we'll end up, after we simplify this thing, with the following generalized non-deterministic finite automaton. It's got a single starting state, a single accepting state, and a single transition. And it will be labeled, after the simplification, with a regular expression. And this will be the regular expression that we're looking for that describes our regular language. Okay, so the way we're going to do it, the way we're going to do this simplification is we're going to repeat the following steps. What we're going to do is we're going to choose a state, arbitrarily choose any state. We won't choose the initial state or the final state, but any other state that's not initial and not final, we're going to choose. And then we're going to remove the state, but we're going to have to modify all the remaining edges so that the machine still accepts the same language. And as I said, we're going to repeat this process of choosing a state, removing it, and modifying the remaining edges until there are only 2 states left. And at that point we have a machine that looks like this, and we've identified the regular expression. So now we've converted our non-deterministic finite state automaton. Well, we started with the deterministic finite state automaton actually, so I should probably change this to we converted our deterministic finite state automaton into an equivalent regular expression that recognizes the same language. So here's what we're going to do. We're going to select a state at random, but we won't select the start state or the accept state. Let's call it QRIP, Q sub RIP. And we're going to rip this state out of the generalized non-deterministic finite automaton. What that means is we're going to remove the state, and we're going to remove all the edges that go to and from it. And then we're going to have to modify all the other edges so that the resulting machine still accepts the same language. Okay, so here's a machine, initial state, final state, and it's got 4 other states with full interconnectivity. We're going to choose some states, such as this one right here, and we're going to remove it and all the edges that go to it and all the edges that go away from it. So all the edges that are in red will get removed, and we'll simplify the machine by modifying all the remaining edges. That is, we'll modify all the edges that are in green. Now, when we pick a state to remove, we have to modify the machine so it accepts the same language. And it turns out we have to modify every remaining edge that's in the machine. We remove all the edges that were connected to the state that we're removing, but every other edge has to be modified. So it's a rather complex process. So consider 2 states, okay, and we've chosen some other state in the machine to remove. But just consider 2 arbitrary states, okay, Qi and Qj. And there's an edge that's labeled with a regular expression. Well, now we've decided to remove some other state, okay? Subsequently, I'll call it QRIP, subscript RIP for ripping it out. QRIP, okay? So we could have gotten from I to j by going through this other state. So here I'm trying to portray that, okay? So here is I and here is j, and there's an edge before, okay, we remove some state, and we can get from I to j by going directly along this edge that's labeled with a regular expression R4. Now here's our generalized machine. We've got our initial state and we've got our final state. And we're going to choose some other state to rip out, like perhaps this state right here, Q sub RIP. We're going to remove it or rip it out. And you can see I've got all the other edges in the machine, and I haven't really labeled all of them, but they have regular expressions. But notice that there's also a way to go from Qi to Qj by going through the state that we're removing. We could have gone to that state and then possibly taken this transition several times and then taken this one. We're going to be removing this state plus all these edges that touch it. Okay? So we could have gotten from I to j by going through it, and so one way to get from I to j is to go directly, and there's a regular expression that describes all the strings that will take us directly from I to j. Another way to get from I to j is to go through the state that we're removing, and we have regular expressions R1, R2, and R3 to describe those transitions. And so any string that matches R1 followed by 0 or more occurrences of strings that match R2 followed by a string that matches R3 would have gotten us from Qi to Qj. So we need to modify this. Okay? So here I've drawn the same thing. I've ignored all the other edges besides just R4 and the edges in red, R1, R2, and R3. Okay? So we can get to Qi, from Qi to Qj directly, and there's a regular expression that describes those strings. And we can get from Qi to Qj by going through QRIP, and the regular expressions that describe those edges are labeled R1, R2, and R3. Okay? So when we remove this state, we need to modify this edge, okay, to indicate the 2 different ways of getting from I to j. And so we modify the label on this edge to become the regular expression R4 or, and then all these things group more tightly. So either R4 or R1 followed by 0 more occurrences of R2 followed by R3. So we build a new regular expression to describe what strings will get us from state Qi to Qj now that we've removed the state Qrip. And remember, we have to do this to every possible edge. So there's also a way to get from Qk to Qj. Okay, you can either go this way, or we could have gone along this edge, through this, and then along R3 edge. Okay, and we could have also gotten from Qj to Qi, going in the other direction by taking this edge here, and then 0 more occurrences of R2, and this green edge down here. So we have to modify not only this edge R4, but every other edge that remains. This edge, this edge, this edge, this edge, this edge, and all of these edges as well. But for each one of them, we make a similar modification. Next, let's look at an example of how we can perform this simplification and get a regular expression to describe the language. In the course of this, we're going to be creating some rather complex and ugly regular expressions, and we'll want to simplify these regular expressions as we go along to keep things from getting too ugly. So let's notice that there's some simplifications we can make. If you've got an empty string concatenated to some other stuff, you can just eliminate that empty string. Okay? An empty string followed by some other string is just that string itself. If you've got the empty language concatenated with something, then that is just the empty language. You choose something from this set and follow it with something from the second set. Well, there is nothing from the first set, so there's nothing to choose, so nothing can satisfy that, so it's the empty language. So if we see the empty symbol here in concatenation, we can eliminate it. Also, let's look at empty or regular. Well, that's just the empty language, which is the empty set union some other stuff. Well, that's just the stuff itself. So we can also eliminate this. So this will allow us to simplify our regular expressions, and so they don't get too long. So here is a regular language described by this machine. It has edges 0 or 1, followed by 2, followed by 0 or 1. So we can see the answer we want to get pretty clearly. What language does this machine accept? Well, it's a 2 preceded by 0 or more occurrences of zeros and ones in any order. So 1, 1, 0, 0, 1, 1, 1, 0, 0, 0. And likewise, we can stop after we've seen the 2, or we can throw in some more zeros and ones. So here's a regular expression that is our desired answer. Now let's look at how we can use our algorithm to derive this regular expression from this machine. We begin with our deterministic finite-state machine to describe the regular language here. And the first thing we do is we convert it into a generalized non-deterministic finite automaton. We add a new starting state, which I'll call A, and a new final state with epsilon edges. Okay, and then we add all other edges. So between every pair of edges, between every pair of states, we need an edge. So from all of the other states to the final state, we have edges labeled empty set, and from the initial state, we have these edges. And finally, we've got an edge here that's we've really got two edges from B to itself, one labeled 0 and the other labeled 1. So we combine that into one edge labeled 0 or 1. And the same thing with these two edges here. We combine it into one edge here. Okay, so now there's our generalized non-deterministic finite automaton. Now let's just arbitrarily choose B to remove. Okay, so I've removed B and the edges that connect to B, leaving all the remaining edges. and each one of those has been modified. So let's go through each one of those. To get from A to C, we have the empty set, but we could also do it by going the empty string followed by 0 or 1 followed by 2. So empty string followed by 0 or 1 starred followed by 2. And we can use our simplification to simplify this to just 0 or 1 star 2. What about, let's do this edge from C to D next. Okay, it's epsilon, so it is modified to be epsilon or, and we could also get to D by going through B, empty set followed by 0 or 1 starred followed by empty set. So that's empty, 0 or 1 starred followed by empty. Well, concatenating empty to anything eliminates it, so this reduces to just the empty string. What about this edge from C to itself? It was previously labeled 0 or 1, so it's 0 or 1. But there's also a way to get from C to itself by going through B. Empty set, 0 or 1 starred, 2. Empty set, 0 or 1 starred, 2. Well, because this empty concatenated with anything, it eliminates it. This reduces or simplifies just to 0 or 1. And let's see, we have an edge from A to D, labeled with the empty, but we could also get there by going through B. Empty string, followed by 0 or 1, starred, followed by the empty set. So in addition to this empty, we could also say epsilon, 0 or 1 starred, followed by empty. 0 or 1 starred, followed by empty. Simplifying this all down, it's also empty. So now we've got only 4 edges left. Now we're going to clean up our diagram a little bit so that we can work a little bit with it. So this simplifies to 0 or 1 star 2. This is just 0 or 1. This edge from C to D is epsilon, and then from A to D it's just empty. Now we choose to rip out C, the only possible choice at this point, because we cannot choose the initial or the final states. So the only other state left is C. We're going to remove that. So the only edge that's left is the empty edge here, but now we had a way to get from A to D by going through C. 0 or 1 star 2, followed by 0 or 1 star, followed by empty. So that's 0 or 1 star 2, followed by 0 or 1 star, followed by empty. And if we simplify that, we get the empty goes away, the empty string goes away here, and we get 0, 1 starred, 2, 0, 1 starred, which is exactly the answer we were looking for. So we've shown an algorithmic way to take a deterministic finite automaton and to convert it into an equivalent regular expression. So this completes the proof that the class of languages recognized by deterministic finite state machines and non-deterministic finite state machines and regular expressions is the same. They're all equivalent in their expressive power.